Hello, everyone, and thanks for joining us today for the webinar. The title is Meet the MobiSpaces Use Cases, Innovations for Urban and Maritime Domains. I'm Matteo Farsetta, Project Manager of the project from GFT. The project counts more or less 25 partners, and it's research and innovation action from the EU. As of myself, I represent GFT Technologies, which is a company that works in the financial sector as a system integrator, but we also usually coordinate European projects, as in this case. Well, I think we are ready to start. So, as you might have seen, this is the cover of our webinar. It is starting now, and it will last 1 hour and a quarter time. And these are the panelists. So there's myself, Matteo Farsetta. Then I leave the floor to Christos Dulkeridis, our technical coordinator. And we will then proceed with the use cases with Lorenzo from AMT, Gabriel from Bosch, Constantina from MT, Ona from Frequentis, and Ove from the Danish Geodata Agency. They have different backgrounds and different expertise, which makes the European projects always very, very interesting because of the many different competencies put in place in order to reach a common goal. So this is the webinar agenda. We've been having the general overview, then the project overview with Christos, and then we'll proceed with the use cases and the closing. Some rules. First of all, here you can scan the access to check out our website. The overviews will take up to 5 minutes, and then the use cases presentation will last 9 minutes each. And at the end of each use case, we'll be having a main question. Then the other questions also that you are invited to place in the Q&A section will be addressed in the closing moment. And the question that will not find an answer during this webinar will be answered at a later stage with a different tool, such as a newsletter or a direct mail. Now, this event will be recorded and will be available within the next 24 hours. You will find also the PPT presentation, everything on the website. And as I said, the interactive chat is available by default, and you're encouraged to use it, as the speakers will be pleased to answer back your questions, also live when possible. You can follow the chat and be informed and receive links to further follow-ups and details on the project. And you're kindly invited to subscribe to our newsletter to be updated. So enjoy the webinar. I leave the floor to Christos for the project overview. Thanks for being here.
Thank you, Matteo. I hope you can see my screen now. So my name is Christos Dulkeridis. I'm an associate professor at the University of Piraeus in Greece, and I'm the technical coordinator of the MobiSpaces project. And I will give you a brief overview of the project. So the title of the project is New Data Spaces for Green Mobility. So the idea is to present, to deliver a data space for mobility data. The project started in September 2022, and it will last for 3 years. It was funded under the call Data 0101, which is about technologies and solutions for compliance, privacy preserving, and also responsible data operations. And the project is fully funded 100% by the EU. We are a fairly large consortium of technical partners. There are large industries, European industries, which are part of the consortium, but also academic partners. We have more than 10 technical partners with diverse expertise in different areas such as big data management, machine learning, artificial intelligence, data science, but also in issues related to cloud, fog, and edge computing and IoT. Also, in the consortium, we have 5 use case partners who are pioneers in maritime intelligence, and also we have urban and maritime authorities who are part of our consortium. And the focus will be on 2 mobility domains, first in the urban domain and also on maritime domain. So the vision, what's the vision of MobiSpaces? The vision is to deliver a mobility-aware and mobility-optimized data governance platform so as to utilize the outcomes of AI-based mobility analytics and optimize the complete data path. By data path, we refer to the entire life cycle of data, from data acquisition to data transformation, data processing, and eventually data analytics. So the focus in MobiSpaces will be on effective and trustworthy data governance, also on optimizing energy consumption, and this will lead to minimizing the carbon footprint, which is it's of big interest for the EU. Also on efficient AI-based data operations, and all that while enforcing secure data handling, privacy preservation, and also compliance to regulations such as GDPR. Also, we need to support standardized data sharing and interoperability between different applications. And there is also a strong focus on decentralized processing and analytics and moving processing and analytics from the cloud and towards edge devices. We have 5 main technical objectives. The first one is to deliver the data governance platform for trustworthy and reusable data operations. The second one is about green and AI-enhanced data management. The third refers to end-to-end declarative analytics for heterogeneous data sources. So the idea here is to use a declarative language like SQL to query data irrespective of where it is stored. The fourth objective is to combine batch and real-time analytics and have a high-performant solution. And the fifth objective is about explainable AI, federated learning over mobility datasets. In the figure, you can see in the center the mobility data space, along with its 2 main offerings, the AI-based Data Operations Toolbox and the Edge Analytics Suite. The first one, the Toolbox, comprises different solutions for data operations, such as declarative querying, decentralized data processing and data management, and also Online Data Aggregator, which is very useful also for preserving privacy. And on the other hand, the Edge Analytics Suite comprises diverse analytics functionality, such as explainable AI, federated learning, as well as visual analytics. On the top, you see also the green environmental dimensioning workbench, which is responsible for monitoring the energy consumption of data-intensive operations and sending and providing information to our platform for more intelligent placement of data processing and analytics tasks. And we have 5 exciting, I would say, use cases. The first 2 come from the urban domain, while the other 3 come from the maritime domain. The first one is about predictive maintenance and service analysis, and this affects fleets of buses, as you will see. The second one is about intelligent infrastructure traffic sensing. And then we have the 3 maritime use cases. The first one is about edge-powered vessel tracking. The second maritime use case about edge computing on moving vessels. And the last one is about enhancing nautical maps by means of crowd sensing which is very important for safe navigation. So without further ado, I would like to pass the floor to the more interesting part of the webinar, which will be the use cases themselves. Thank you very much.
Thank you, Christos. So we are moving to the first use case with Lorenzo presenting from AMT. Lorenzo, the floor is yours.
Okay, thank you, Matteo. Thank you, Christos. It's Lorenzo Mantero from AMT. I hope you hear me well and you see my screen. AMT is the use case leader of the first use case of MobiSpaces that is called iRoute. And it is set in the city of Genova, Italy, where AMT is the local public transport operator. Our use case will face with a growing electric fleet of our city. AMT has 650 buses, of which 100 are electric. But in the next years, this fleet of electric buses will grow. There is a big project for the next year to buy almost 145 new electric buses to cover all the 4 main bus lines that go across the city of Genova. So a fleet that is growing, and also some peculiar problems of the electric buses that are growing. And we are glad that we can participate to MobiSpaces project with a use case focused on green mobility in order to try to face these problems and to be ready also for the future that for AMT will be full electric. We decided to face 2 main aspects of electric fleet management that are maintenance and service management. And so we divided our use case in 2 main themes. The first one regards predictive maintenance. Predictive maintenance consists on the analysis of how some typical malfunctions of buses have occurred during the years in order to try to predict when and how the same malfunction will occur again to the same bus. In our use case, we will focus on doors that usually generate many problems since they are a very stressed component of the bus. But also we will focus on a peculiar problem of e-bus that is battery temperature in order to face fire risk. Then the other theme is what we call predictive service analysis, that actually is the monitoring of energy consumption and battery decay, that are 2 problems related only to electric buses. And are made of 2, we divided in this part of the use case with 2 objectives. The former is a long-term analysis in order to develop new bus timesheet that have to be optimized in function of the usual battery behavior and decay during the years. The latter is a real-time analysis that aims to determine the possibility for a bus that is going around the city to end its schedule with an acceptable battery level, considering many data. So, for example, its path and schedule, the real-time battery level, but also some external data that have a strong impact on the battery level, such as weather and traffic. So there is a big amount of data, but the problem is not actually having data, because public transport companies usually have a lot of data. The problem is how to manage them, how to use them, how to make them talk to each other and talk back to you saying something useful. So what are these data that we use as an input for MobiSpaces platform? We start from AVM. AVM is an automated vehicle monitoring system. It gives the location of every bus of the fleet every 30 seconds. Actually, there are 2 data flows. One allows our bus control center to know the real-time situation, so to know the location of all the buses every 30 seconds. There is another data flow that starts at in the evening when the bus comes back to the depot. And this second data flow collects all detailed information about all the trips, all the stops, all the numbers of passengers, and also the possible problems occurred to the bus during the day. So it's a very useful kind of data that can be used to make analysis in MobiSpaces. Then there is another data that is GTFS. GTFS is a Google standard that maybe every one of us uses, even not knowing it, because Google uses GTFS to show us the bus or also underground all transport timetables. So when we look for a trip on Google Maps using public services, Google Maps has GTFS data inside. So they can be used in general to know the program service of a public transport company. There are also GTFS data real time that show the real position of the buses, so show the delay, or for example, they can also calculate through GTFS real time. It is possible to calculate the waiting time at bus stops. Then there is maybe the most important kind of data that we have for MobiSpaces project, that is CAN bus. CAN bus is a system that collects most of functional parameters of the bus, for example, also battery level, and send this data to the bus control center. So this allows to make analysis on the behavior of the batteries, but also of many other functional parameters or bus systems. And so this is the center of both of the predictive maintenance, of which I was talking about, and of the predictive service analysis for e-buses. Finally, we decided to use some external data because we saw that they have an impact on the behavior of the battery. These data are weather and traffic data. All these data enter in MobiSpaces platform that has a powerful data analysis tools and artificial intelligence tools, of which Christos was talking about in his presentation. And thanks to these tools, we can have some outputs that are very useful for our service management of every day. These outputs are mainly a short-term prediction on battery level. So we know in real time if there can be problems to our fleet or to a bus, and we can manage promptly we can act promptly in order to reduce as much as possible inconvenience to passengers. And then there are the long-term analysis, of which I was talking about, for example, for the optimization of e-bus schedules. Finally, there is the prediction of some malfunctions that can reduce the causes of disruptions, the cases of disruptions of service. All this brings some important results, both in terms of performance of AMT, of our company, both in terms of quality perceived by the users, because an optimization brings also preventions of maintenance problems, of low battery problems, and finally, the reduction of bus waiting for end users. So something that improves the travel experience of our everyday passengers, AMT passengers. That is our mission and what we want to do. And so we thank MobiSpaces to help us to reach these objectives. Thank you.
Great, Lorenzo. Thanks a lot for the presentation. Just one question for the audience. Since this use case will have a huge impact on people in their daily life, how many people will be impacted and what will directly change for them?
Okay, thank you. I may come back to this slide. I start saying that many people can use the achievements of this use case, because nowadays on the e-buses fleet of AMT, almost 20,000 passengers every day can travel on our e-buses fleet. that are almost 6 million passengers every year. But as I was saying before, in the next years, this electric bus fleet will increase, will reach mainly the 4 most used lines of the city on which travel more than the 50% of our passengers. So really, many citizens of our city will use these results, because MobiSpaces help us now also to be ready for the future of AMT. And what passengers can appreciate is that there are less disruptions of service. So the less malfunctions, less problems related to bus changes for battery problems. And in general, and if the system is more efficient, everybody can appreciate this efficiency. So everything works well, and also the quality perceived by the end users is much better than now. So thank you.
Great, thanks, Lorenzo. So now we move to Gabriel's presentation, so use case 2 from Bosch, SmartSense. Gabriel, the floor is yours.
Right. Can you see my screen?
Yes.
Okay, great. So my name is Gabriel Braun. I'm project leader for the SmartSense use case from Bosch. And I will present to you our use case. So, sorry. So SmartSense is all about air quality. So according to WHO, we have 4.2 million deaths of poor air quality every year. In Europe, bad air quality can be found mainly in urban areas, where traffic is one of the main contributors to bad air. So in our use case, we will try to improve traffic-induced emissions in a test field in Thessaloniki in order to most efficiently plan necessary measures to reduce traffic emissions. What is needed for that is a modeling which is based on 20-meter segments of the roadside traffic, a simulation of the dispersion into the neighborhood area, and also we will put up 9 air quality monitoring sensors in the testbed of Thessaloniki. What we will do with this data is capture the traffic situation and emissions. We will be calculating the emissions and dispersion and measure air quality. We will pass on this information to the traffic management company or to the traffic management system of Thessaloniki. Based on the data, we will plan intelligent measures with air quality and traffic data analytics. And then we will switch an environmental sensitive active traffic management strategy in order to reduce the emissions. Then we will basically go into this loop again and improve as long as we have reached our goal. So let me show you our test bed in the city of Thessaloniki. So it's a test area which is 1.8 kilometers by 2.5 kilometers, located in the center of Thessaloniki. So it's a very crowded urban area. And in this test area, we will model the dispersion. We will put up 9 of these air quality monitoring sensors, which you can see in this picture. And we will, of course, model the traffic emissions in order to reduce on that. So this air quality monitoring box measures gaseous emissions such as NO2 and O3, and also particles such as PM2.5 and PM10. It also measures other data such as relative humidity, temperature, and pressure. All right, so let me give you an insight on what we exactly want to do to improve traffic emissions. So on top, you can see the influencing factors for traffic emissions. So there's traffic volume, there's the traffic situations, so like stop and go or fluent traffic, and of course there's acceleration. So the factors, the traffic volume and the traffic situation influence the emissions linear. But if we go to accelerations, we have a much higher influence of the acceleration. So the factor is 4 to 10 compared to 1 for traffic volume and for traffic situation. On the lower end of the graph, you can, or on the slide, you can also see the mean NOx emissions compared constant driving and accelerated driving. And what you can see is basically the accelerated driving outnumbers the emissions of a constant driving by far. So what we want primarily to do is to reduce the accelerations in the traffic, and by that reduce the emissions by far. So to give you an example of what we have already done, so this is Stuttgart Negator. It's one of the main, most polluted spots in Germany, and we have already done some tests there basically. So what we did is we reduced the speed limit from 50 kilometers per hour to 40 kilometers per hour. And we also installed 2 speed cameras to enforce that speed limit. And what you can see is basically in these 2 curves is the emissions. So after the traffic light, you got a very high emissions due to the cars being accelerating. And after we introduced this new speed limit reduced to 40, you can see that you get lower emissions. And in some, it's about 20% lower emissions. So basically, this is something what we also planned then for Thessaloniki, to reduce the acceleration and by that reduce the emissions, and so improve the air quality in this test area in Thessaloniki. All right. So what are the main challenges for MobiSpaces? So first of all, if you think about air quality measurements, you have to encounter that you basically measure nothing. So the concentrations which we are measuring here is in parts per billion. So it's really minor concentrations what you try to capture. And there is a lot of side effects to that sensor measurements. And to reduce the side effects, we have to have intelligent algorithms which are running on our air quality measuring boxes, and that we want to improve in MobiSpaces. We also need a comprehensive modeling of the traffic emissions that reflects the acceleration of the emissions, which is not a standard. Another challenge is the complex air dispersion in urban areas. So there is a lot of buildings, of course. So it's also so-called street canyons, which you have, which makes the dispersion of the emissions very complex. So this is another challenge, and we will generate a huge amount of data with our models, and this has to be processed accordingly in order to improve the traffic reduction, to improve the traffic emissions by 10 to 20% in that test area. So these are the main challenges, and what we expect from MobiSpaces is exactly what I already said, is improved accuracy and reliability of our air quality measuring devices by using the help of the MobiSpaces platform to develop intelligent algorithms. We expect to have a more efficient data processing of emissions and air quality data. We want to derive further insights on effects and possible measures to improve air quality. And we want to prove an emission reduction in this test area of Thessaloniki. All right, so that's basically it.
Thank you.
On my side.
Thank you, Gabriel.
Okay, do we have 2 questions for Gabriel in the Q&A section? So the first one is from Bartos, and he's asking, do you take into consideration non-tailpipe emission as well?
Basically, yes. So we are planning to also, right now we are not doing, but within MobiSpaces, we are also planning to use tire wear and brake wear as emissions. Yeah.
Okay, and we have another one which from Mahmoud, which is asking, in the second use case, how is the traffic volume situation observed? In other words, what is the input for building the traffic models?
So it's basically two inputs. It's traffic volume, which we get from the traffic counters from the traffic management system, and there's so-called floating car data. So it's basically from some cars we will get 1 Hertz data of the vehicle speed that are driving in that area, and this 2 data can be combined as an input to a traffic to an emission model to calculate these emissions.
Okay.
So it's basically GPS data which we use basically for that, and this we get not from all cars but from some of the cars. We are getting this data from a data provider.
Thank you, Gabriel.
Thank you, Diego, for raising the questions from the chat.
We have another problem, yeah, from Mahmoud. If you prefer, Mahmoud, we can give you the, okay. Is it possible to use satellite imagery of air quality instead of self-deployment emission sensors?
Can you repeat?
Is it possible to use satellite images of air quality instead of self-deployed emission sensors?
No, it's not possible due to the resolution. So the resolution of satellite information is far too coarse to capture the effects.
Okay, perfect. This was the last one. We need to move on.
Yes, please. And thanks, Mahmoud, for the questions. In any case, if you want to reach out, there are many channels such as the official website and our contact emails. So now let's move on to use case 3. Constantina, the floor is yours.
Thank you. So hello, everyone. I'm Constantina Bareta. I'm a researcher at MarineTraffic. I will present to you the empty tracker use case of MobiSpaces. So MarineTraffic leads this use case. MarineTraffic is the world's leading platform for offering vessel tracking services and actionable maritime intelligence. MarineTraffic.com is an end-to-end service that tracks vessel positions based mainly on the automatic identification system, also known as AIS, and displays them on the map in real time. So this is a typical day at MarineTraffic in numbers. We have to process nearly 70 gigabytes of streams of AI-based data in order to serve approximately 1 million users. So as I said before, we are based on the automatic identification system. This is a collaborative self-reporting system that allows marine vessels to broadcast their information to nearby vessels and then ground-based stations. It is based basically on VHF communication, and it is used for vessel traffic monitoring and maritime event detection. Initially, it was established in order to avoid collisions between vessels. However, it proved to be a valuable source of information, and it now bases many maritime applications such as marine traffic. However, AIS is not mandatory for all vessels, and while some vessels bear AIS transponder, they switch it off in order to, for example, engage in illegal activities. These are known as dark vessels. In other cases, some vessels might experience equipment malfunctions, or they might navigate into an area with low coverage. So again, we cannot track them down using AIS. So the objectives of this use case is first to develop a robust and accurate vessel tracker to resolve measurement to object association ambiguities, especially in cluttered multi-object scenarios, as for example in a port with a lot of traffic. Also, we aim at developing techniques for multi-sensor, multi-object tracking in order to enrich information coming from different sources. So for example, as we cannot track all vessels using AIS, we can use complementary sources for vessel tracking. Last, we want to combine the results at the regional level, providing macro analytics on aggregated data from edge devices, reducing costly data traffic transferred to centralized infrastructures. So these are a description of AIS data. We have Class A transceivers and Class B transceivers. The vessels that are commercial and exceed 300 tons of and travel internationally are obliged to bear Class A transponders. So we get both static data, static messages essentially containing information like vessel name, vessel type, MMSI, and so on, and also voyage-related data, such as draft, cargo, ETA, and so on. The dynamic data are related to the navigational status of a vessel, its coordinates, the course, heading, and so on. So another source of data that we will use in the context of this project is the RF data. Basically, we detect nearby radar transmissions using two bands, the X band and the S band, that are supported by the vessels. And we correlate the detected incidents with AIS in real time in order to reveal dark vessels in the area. That is, vessels that do not transmit AIS messages, but we can track them down using the radar transmissions. For safety reasons, it is not very likely that a vessel switches off its radar transmissions as well. So we perform edge computing. We perform a multi-sensor, multi-object data fusion on the edge device. And we perform also fingerprinting on radar transmissions as we're trying to associate the unique RF, the RF signal, a unique signature with a specific vessel without using the AIS data. So this is the first version of our architecture. It is very high level. So in the context of the project, we will experiment with two sets of edge devices, each one including an AIS data receiver and an RF data receiver. So we will get two streams of data, one from AIS and another one receiving radar transmissions. For each one of these streams, we will do some pre-processing on the edge device. So for example, for AIS data, we will do timestamping, decoding, and we will merge static and dynamic messages. And for the other stream of data, for the RF data, we will do some down conversion. We will try to convert RSSI to distance conversion. So for example, the signal strength that will be converted to georeferenced targets identified through the radar transmissions. So then having the two processed streams of data, each one containing georeference points, will be served as input to the first part of our fusion engine, the position to track association. So we will associate positions of targets to known tracks. This will also take place on the edge device. Then the output of each of the two processing chains will be served to the track-to-track association. So in this way, we will be able to identify tracks that belong to the same trajectory. The output of all this processing chain will be global unified tracks consisting of positions coming from AIS and RF data. So the KPIs that we have in this use case are three main KPIs. First of all, we will perform data to object association accuracy above 85%, data to track association accuracy above 80%, and data to server load reduction above 30%. So this is all from my side.
Thank you, Konstantina. Just one question for the audience. How will MT benefit from the MT tracker, and how will it be exploited?
Thank you, Matteo. Marine traffic already has a large amount of data, AIS data. We have the largest terrestrial AIS network, which we complement with third-party satellite AIS data. But in our product, we have not yet targeted the problems of low AIS coverage and the problems of dark vessels. This is something that a lot of our user segments need, and this is a need that they have already expressed to us. So it is the first time that we will be able to tackle this need using reliable complementary sources, such as the radar transmissions. The radars are, I think, the most reliable source of vessel tracking information that they use in the vessels. So in the vessels bridge, when they want to see which vessels are nearby, they're using the radar, and they're using complementarily the AIS. So we want to move what is offered on the vessels bridge on a web-based maritime application, such as MarineTraffic, which will be available for everyone.
Great. Thanks a lot, Konstantina. We shall move right now to the next use case. So, Dabi, the floor is yours.
Hello, everyone. I am sharing my screen. I hope you are able to see now.
Yes.
My name is Leonardo B. I am solution architect in Frequentis. This is the fourth use case of the MobiSpaces vessel edge computing on board of moving vessels. We are running this project with Austrian Institute of Technology, thanks to Anita Gracer also. She's contributing our project a lot. As a Frequentis maritime division, we are providing control center solutions for situational awareness. So how we see maritime domain, you can see on top of the picture, and we are providing GMDSS, search and rescue, VTS, and coastal surveillance services. Our product suite, Frequentis Matrix solution, covers all of them, and AIS is one of the important part of this capability. Situational awareness all depends on this. But the main issue is usually our users have AIS information, as you can see on the left side of the picture, coastal surveillance is easy because there is terrestrial AIS coverage. But on the open sea area, usually it depends on satellite AIS, and latency is more than 3 to 4 hours. As a result, you would like to improve their situational awareness. As an operator, they can see on their screen, let's say this is the open sea area, they will not be able to see anything on this area. With this project, we are aiming, one of our organization's vessel is there. We can integrate our far edge device on the vessel, and operators will have situational awareness of this area. So, as user story, we are targeting to improve situational awareness for operator by developing mobile sensors to overcome limitations of the access, bandwidth, location, time, and we can stream real-time information to the operators. Additionally, in the future, possible additional use cases, we can share data sharing, learning between different operating entities, and control rooms, different organizations. So we can enrich the model with other data, whether TDAL or other data, and same application provide model for other applications. If we go back to maritime domain visualization, we can visualize our project like this on the open sea area. Vessels mandatorily they have vessel AIS receivers, so we can use this data and we can process this data on board unit, and with the onboard unit we can transfer this to the near edge servers, so we can make the backward process and it can be visualized on the operator panels. When they wish, when the operating party wish, they can share with the other organizations same information, and they can improve their model. So as a project KPI, successful development process, we get the raw AIS data stream, transmit the K model as a local model back to the control room, and we are extending coverage beyond reach of the coastal AIS antennas. Coverage and there's a connection limitation. If we can compare the data rates of the satellite is 38.4 kilobit per second. Our target makes the bandwidth usage to 3 to 32 kilobit per second, and our gain will be 5 to 10 times, depends on how we're gonna use. And latency on the satellite is 3 to 4 hours. And with our compressed data modeling, it could be less than 5 seconds, so we will gain 1,000 times more. So for the infrastructure and communication link characteristic, as I mentioned earlier, on the vessel side, we are using existing vessel AIS receivers. We would like to process with Raspberry Pi or Intel NUC. We don't want to be limit ourselves, depends on the process power we need. And as you can easily suggest, we will use NMEI serial interface. Get this, we will process the data, decode the data, and we will transmit with the satellite or VDAS, and we will transmit we will simulate MFHF transmission. So if you compare coverage, our main limitations is the data bandwidth, and to do that, we need a more efficient data compression and priority for the sharing data. As an architectural logical point of view, we got the raw AIS data, we decode it, and our model detected local anomaly detection. We train our model, we'll compress this data and send it to the near edge servers. Near edge servers reconstruct the same thing, and it will integrate to their model, and the operators could visualize this. Important point is our machine learning based model will prioritize which one is the highest priority. This will lead us to send the most important data in case of we have bandwidth limitations. As I mentioned earlier, in case of they would like to share their data with the other organizations, they can we can combine on the higher cloud and the other organizations together. So we are sharing dynamic data locally, and JSON over WebSockets. We will publish subscribe button. Position information, of course. Static data will be on the edge computers, and we will request. And trajectories of the vessels will be in exchange between the models, and model will create the main structure. As a deployment diagram, AIS data will be get, NMEA data will be decoded. Algorithm will calculate the trajectory, extraction, and data propagation. With the demodulation, we will be sent to the transmission system, and they received. Vice versa, working will be working and visualize on the operator panels. And on the cloud side, we can share with many other organizations. Thank you very much.
Thank you, Debbie. We have a question from the audience. So what is the desired compression rate of AIS messages?
Actually, rather than compression rate, we would like to fit in the HF communication, MF-HF communication for the worst cases. We would like to optimize trajectories by the model algorithm. And we don't want to send the full AIS data over there. Models should create the trajectories on the both edge computers.
Great. And then another question. Do you have access to the vessels? How many vessels are you planning to make tests on?
As you know, we are working with many organizations together, search and rescue organizations. They are operating on the open seas area, GMDSS organizations, so we have access to them. In the part of the program, we are planning to use 3 vessels. We would like to run it on the 3 vessels. We are talking with the organizations to arrange this during the project.
Okay, great. Thanks a lot, Abby. I think we can move to the last use case from GST. So, Ove, the floor is yours.
Thank you. Yes, hello, my name is Ove Andersen. I work with the Hydrographic Office in the Danish Geodata Agency, and we are the lead of the 5th use case called CrowdSeaMapping. So the Danish Geodata Agency is responsible for making nautical charts, and a nautical chart is a map of the sea area where you are ensured that this map is the most up-to-date information we have of the certain area where you are sailing. So it's a safer navigation map we are providing and selling for the entire area of Denmark and Greenland. So whenever you're a big ship and you're going to sail within these areas, you're obliged to buy a map to have a safe navigation while you're sailing here. We also make other products like a depth model. You see this here on the right. This is a complete depth model of Denmark, where we have a depth information, including other metadata for the entire nautical area of Denmark. And this is a public available model we generated to make some data available for other partners in this project and for other research institutions to actually have some data and information you can work on. Historically, nautical data and marine data has been a secret of like a national treasure, because this is the key information for actually approaching country. But now collecting data is more and more becoming something most people can do, and we are more focusing on making safe navigation products. So far, the source of data for nautical charts has mainly been the Danish Navy or other agencies like the Environment Agency, collecting data when they are investigating sea bottom. We also get from commercial companies when, for example, the wind farm is to be put up in the nautical areas. But this looks very nice, this model, but not everything is wonderful and unicorns. This is the truth if we dig a bit into our depth model. So here you can see that only the green areas, the 18% of the Danish area, is actually high quality multi-beam sonar data. So these data are made with the recent acquisition equipment, and you have a centimeter precision quality both and precision both horizontally and vertically. But some of the challenges is that it's quite complicated making such high quality surveys. Both the survey seasons are short, we have limited resources, and we need to cover both the Danish areas, which some think is rather small, but also the entire Greenland area. We are obliged to do our best effort to collect data. So 18% of the data we have in the Danish territory is high quality data. Then we have 6% of the data which is historic data dating back from the actually 1850s, 60s, starting with lead lines, and you only georeference yourself with physical positions on land. Then we have some single beam older equipment, and still we're using this in the nautical maps. And of course, this is not the perfect data foundation, but this is what we have. And then 76% of the area in the Danish territory is actually interpolated in this model. And this might seem a bit worrying, but still in these areas, the water is quite deep, so you won't hit a rock or something in this. There's hundreds of meters of water below you, but still it's unsurveyed territories. So we would like to see, can we actually do better? Therefore, we are looking at what's called crowdsourced bathymetry. And crowdsourced is just like, you know, from Wikipedia or OpenStreetMap, you make the crowd do the work for you. So the crowd is collecting data, and they're providing data for you to actually make better products. And hopefully the crowd will actually also gain something from the data they're providing for you. The advantage of crowdsourced data is low cost, and it's relative reliable bathymetry data loggers that we have on board vessels. It's still professional equipment, and the coverage is wide. Some of the challenges with crowdsourced data is that communication while you are not on land, as we just heard, is slow and it's expensive. And often you're actually offline, especially if you're going on a longer voyage, like from Denmark to Greenland, then you're offline most of the time, unless you have an expensive satellite communication. Also, the equipment is unmonitored and often put there and nobody's monitoring. So what happens if the equipment fails or sensors become unreliable? So it's also difficult to quality assess the data. But the potentials of collecting data from crowds are shown here. So this is 1 year of data from the Danish monitoring authorities of AIS data. So you see that there's quite a big coverage of actually the Danish territory, also where we were only having interpolated data. Class A, SOLAS, AIS vessels mainly cover the main passages. These are big vessels that are obliged to also use our nautical maps for safe navigation, but also Class B AIS information is quite interesting because these are smaller vessels, and these are actually going into shoaler water where we don't have that much water, and they're covering a majority of inland water. So these make it possible for us to actually get information where we have no information today. So the objective of our use case is to do in-situ data processing on the vessel, because we are offline, as mentioned, most of the time. So can we collect and process data decentralized? Can we quality assess the data while we are still on the vessel? And if we can we then assess the criticality of the data in situ while we're on board the vessel? And if we can do these things, then we can start to optimize our communication pattern. We can determine what data is important for us and what can we live. If we don't ever get this data, it's okay. But if you know there's a rock and there's only 5 meters water below you and there should be 20 meters, then we would actually like to know this as soon as possible. And we see federated learning and machine learning can support this quality assessment of data to make a model, decentralized model, where you are learning from the local sensors and local environment you are in, making as good as possible data assessment model, and then figure out when do we need to send data back to us. And we hope that this will address the challenges mentioned before with slow and expensive communication and often offline, so you can prioritize your data, which we need to know as soon as we have some kind of communication link. And also that this model can train itself to actually become an agent that lives offline and unmonitored, but it trains itself and learns and improves itself to actually live decentralized on the vessels. So for this use case, we have been working together with a company called Sternler. Sternler is actually working very much on VDIS communication part. They would like to communicate via satellites for the VDIS communication platform, and they have provided us with a hardware platform developed in collaboration with us on using a Raspberry Pi. And the focus has been on making a low power consumption device where we can put our software, our prototypes on board the MobiSpaces prototype and test out what is possible when we actually put something out on a vessel. This box takes away all the complicated parts with the communication and interfacing with the sensor data on board vessels. And we see this as a very robust piece of hardware where we can put our software and focus on what we are good at, and then Sternler can focus on what they're good at, namely making hardware and making communication work, even if it's VDIS via satellite, base station, or if it's mobile network or Wi-Fi. We can then prioritize what information do we need to send as soon as possible. So this use case hopefully will help us validate our historic data. So if the crowd can help seeing the historic data we have, are these still valid, or do we need to put more focus on resurveying where we haven't done surveying for many years? So we know sand is changed to the seafloor, harbors are being excavated, and the precision of surveying has increased drastically over the last 150 years. So this is the first quick value we see that this MobiSpace use case can help us with. Also, we'd like to detect where are discrepancies, where can we actually detect features below. There's a rock here, we've never been surveying here, but our interpolating model said nothing is here. So this is important findings. Hopefully this use case will help us making more safe and better products. And finally, in the best future, we hope that perhaps crowdsourced data can be a cornerstone in the future nautical maps, or at least nautical products, if not safe navigation, then for other kind of products. Because we see that this is a potential data source that can be so overwhelming for us in a good way, and we can improve our products in a drastic way in the future. But still, we are responsible for the quality in the charts, and we need to figure out how can we use this data and how can we quality assess them, and we are working on it. So thank you for listening.
Thank you. Actually, one question for you as well. How does this use case distinguish itself from the existing initiatives on collecting crowdsourced data?
Well, there are a lot of initiatives actually around the world on collecting crowdsourced data. And these are good initiatives too, where they're focusing on individual areas. But the main focus so far has been on putting devices on board vessels, connecting these with the sensor you have on board vessels, collecting data, transmitting back. Then you do all the post-processing, data cleansing and validation of data, and figuring out what can we actually use these data for on a centralized onshore location. This actually focuses on putting all the post-processing and data cleansing and validation and the quality assessment of data on board the vessel, because we know this communication part is so complicated And we know this thing, putting a USB stick on board a vessel and fetching the USB stick if the vessel is in Greenland suddenly or New Zealand, that's complicated. So can we now have a communication pattern where we can prioritize that information and get what we really need as soon as possible? Then this is very valuable. And then it's okay if we don't get all the rest of the information.
Okay, thanks. Thanks, Ove, for your answer. So since we have some more minutes and there are no further questions from the audience, let's open up a couple of points, use case by use case. So the two questions I am addressing to each use case, and then I ask you to go one by one, is who are the stakeholders targeted by each use case and the project in general, and what is the added value of MobiSpaces technology for your use case or domain? So starting with Lorenzo and proceeding with the order.
Yes. For the stakeholders, I think generally our main stakeholders are our end users, and they are who we want to make their travel experience better. But I also think that we have to use MobiSpaces to think more, let's say, globally. So the electric bus fleet management is something that is not only related to our city, but it's something that every European, at least, city is facing now, because it's really it has a really big impact on the management of a public transport company that not always is ready to change fastly its habits. And so I think that every public transport company can take advantage from the results that MobiSpaces will get in this 3 years project. For what concerns the added value of the technology, as I was saying in my presentation, we have a lot of data, but then MobiSpaces is a project that mainly focuses on managing this data and taking them in the best way, using them in the best way, tries to give us the answer that we expect in the best way. So that's the good usage of our data comes from the technology of MobiSpaces.
Thanks a lot, Lorenzo.
Thank you.
What about Gabriel?
All right. So for our use case, basically, I see, first of all, of course, the main stakeholder, which is the people of Thessaloniki, which are experiencing the air quality within the test area. Then, of course, it's the administration of Thessaloniki, but potentially, so what we want to do is basically, we do not just develop this for MobiSpaces and for Thessaloniki, but we want to basically scale the solution to every city which has air quality issues. So potentially every European city which has air quality problems is a stakeholder. So second stakeholder, I think, is the traffic management system and company, because we need to work closely together with them, because we need them to implement the measures to reduce the emissions, right? So that's the main, the second important stakeholder from my point of view. Regarding MobiSpaces platform, I basically can just agree to Lorenzo. So we will generate a lot of data. So we have to process this data in the right manner. We have to use intelligent algorithms to improve the data, to get analysis of the data. And find the right solution to get the best improvement for the air quality in these urban areas.
Great, thanks, Gabriel. So, Konstantina, the floor is yours.
Thank you. So since what we're offering is an enrichment of our AIS data, everybody using AIS data will be affected. So I would say from mariners to shipping companies, to vessel traffic officers, to defense agencies, Coast Guard authorities. It's a very broad spectrum of user segments. If I had to pick two that would be mostly affected, would be vessel traffic officers, since they will be able to better monitor the traffic inside the ports in highly congested areas, facilitating safety of navigation and also saving time and money for everyone involved in the maritime industry. And also companies particularly interested in dark vessels, such as, for example, insurance companies. Thank you.
Great. And then Dabi.
Our stakeholders directly currently will be the GMDSS, SAR, CSS, and VTS organizations. I believe they will start using directly, and anybody who is operating on the open seas area or anybody related with the vessel traffic will be our stakeholders. They will be able to use our outputs, and they will have a broader situational awareness. They can create a safer, cleaner environment for their users or the responsibilities. And as the other MobiSpaces partner, I believe this data will be able to distribute many of the parts of the world, because maritime domain is very big. Everybody could be using MobiSpaces output.
And what is the added value of MobiSpaces technology according to you for your use case?
Added value is adding to situational awareness for the open seas. Currently, most of the organizations are blind on this spot, or just depend on few technologies. It will enlarge their situational awareness.
Great, thanks, Dabi. Hervé?
Yeah, well, the stakeholders and the value is quite close coupled here. So our user stakeholders are the ones buying our nautical maps for safe navigation. That's the big cargo vessels, that's the passenger ferries, that's everybody who wants to have a safe navigation. And hopefully we can validate all our historic data using this use case, and perhaps even add new data sources to our nautical maps and charts. But even more important, I believe, is that this use case opens up to using a data foundation where we actually start covering areas where we have no information today. So that means we can perhaps in the future make nautical products for leisure sailors and the others who are today buying Garmin equipment, other equipment which have data foundation maps of different qualities. So hopefully in the future we can make some products which are better suitable for the leisure market and the private markets. At the same time, when we start to have better models and opening up our data, like we do here in the production, sharing the data, we become more easily interactive, interacting with, for example, research institutions. They can start using our data, and it's easier to share crowdsourced data than the proprietary data. We can also make new data products for PR, for marketing, and for everybody who actually wants to show and know information of what's below the surface. So we see that having these new data foundation actually opens up for a whole range of new values that can be added in new products. Yeah.
Great. Okay, thanks for your contribution as well. We've had just a couple of minutes of delay, so thank you all for having respected the timing, for being here. So thank you. I want to thank my colleagues who are present and those connected. And I want to thank all the audience for having raised questions and having listened to us. Please join us through the newsletter, subscribe in order to keep posted, and follow us on LinkedIn and the other social. Thanks a lot, and see you soon. Have a nice day.